Multivariable calculus, we're in section 15.5, day 2. Looking at the top, you can see there are two learning targets. I can find the moment of inertia about an axis, and then I can find the radius of gyration about an axis. We need some definitions, and we'll start right here. The moment of inertia of a particle of mass m about an axis is mr squared. And r is the distance from the particle to a specified axis. We apply this definition to a lamina and find the moments of inertia about the x and the y axis. Well, let's say that we were looking at a point, perhaps up here, and we want to go from the x-axis. Well, this distance is, you're looking right here, the distance from that point to the x-axis, it would be the y-coordinate. However, r is going to be the distance, we'd call that y, but I'm going to square it because we're going to need that. And guys, that's what I really want you to see as we're working this definition out, as we're finding that moment of inertia about the x-axis here. Inside the integral, we'll have a y squared times rho times that density function. And, that's really what we're working with today. I think you can see that this is incredibly close because rho times dA is going to get you your mass, of course. But this is incredibly similar to what we did in day 1, where we just found the moment about the x-axis. This moment of inertia, of course, you're just going to square your distance. Likewise, if you were, say, to work with the distance from the y-coordinate, the y-axis, you could see very quickly that that distance would be its x-coordinate, but I'd like to square that distance because we're going to need m times r squared. Again, rho times dA in that integral is going to get you your mass, but when we throw in that square of the distance, that's going to be x squared. So that's something super important for you to just see definition-wise. Now, we also find it useful to consider the moment of inertia about the origin, and that's known as the polar moment. And if we are going from the origin to a point right here, we could call that r, but like all distances, we could say that that distance would be squared in these perspectives. By the way, if x squared's up here, x squared's down below, and I think you can quickly see via the Pythagorean theorem that x squared plus y squared would equal r squared. Well, that's why when you're finding r squared right here, if you're going to find your polar moment, inside, you will ultimately just have the x squared plus y squared as your distance. And furthermore, if you're really looking at these, I think you're going to be able to see very quickly that this polar moment is really just the moment of inertia about the x-axis plus the moment of inertia about the y. If you add those two integrals together, remember those rows are the same, you can combine them into one integral and more or less see this. So that's very helpful as well. Well, they want us to find the moments of inertia for the polar the polar moment of inertia, the moment of inertia about the x-axis and y-axis, a homogeneous disk, a constant density. Rho is just some constant. It's a number like 5. We don't have that constant specified, but we're centered at the origin, and we've got a radius of a. Well, tell you what, let's jump into the polar moment. That seems to be the one, and we've got it right up here. By the way, there should be a double integral right here. Please fix that in your notes. But as we're working this out, as we're working out this polar moment, You could see that this is going to be the double integral over some domain D. That's what we have in yellow. It's that circle. And we'll have our x squared plus y squared times our constant function rho, and here's our dA. And really just want to specify this. We just saw a moment ago that we know that x squared plus y squared equals r squared. That's also a very important link between the polar coordinate system and the rectangular coordinate system. But I'll tell you what, I think this would be a wonderful idea right now to work this integral out in regard to polars. So let's go ahead and take our x squared plus y squared and just call it r squared. Our dA would become r dr d theta. And what about our r boundary? As you're looking in yellow here, you can see we go from a radius of 0 to a radius of a. And how about our thetas? Well, we're going to go between 0 and 2 pi. And now it's just a matter of cleaning this up and finishing this off quickly. This becomes r cubed rho dr d theta. Of course, we could have put rho out in front. And let's just work this inner integral out. As we take our antiderivative, we will bump r up to the fourth. And I'm going to pull rho out in front at this point. It is a constant. And we'll have r to the fourth over 4. And we're going to evaluate that between a and 0. Plugging in a 0, I hope everyone will quickly see that that just wipes out. So we'll have rho a to the fourth all over 4. And at this point, we just have to finish off. This is like a single variable integral problem from before. We've got, theta here, and we're going to go between 2 pi and 0. Plugging in a 0 is going to wipe that out. So ultimately, what do we have? Well, we'll have our rho a to the fourth, let's bring that back down here, times a 2 pi, all over 4. The 0 is just going to cancel out. And what are we really going to see? Well, we're going to see this moment that we've just worked out is rho a to the fourth all over 2. We just found the polar moment of inertia, but we also have to find the moment of inertia about the x-axis and about the y-axis. Now, here's where we can get some help. We can say, remember what we just saw in the notes a moment ago. The moment of inertia about the pole is equal to the moment of inertia about the x-axis plus the moment of inertia about the y. And we just found, this moment of inertia about the pole, the polar moment of inertia. And you can see that we actually have this. But look at this lamina. This is an instance where we can do something really nice. We can say bisymmetry. This is a constant rho. We've got that constant density, and we're going to be able to say that bisymmetry, I sub x would equal I sub y. So what are we really getting at? We can say that I sub x would be half of this, and if we take half of a half, we're going to get a fourth. And likewise over here, we'll have rho a to the fourth all over 4. So that's a little shortcut that we can do. Of course, if you would have worked it out by definition, you would have been fine as well. What you would have had to have done if you wouldn't have used the symmetry trick, you would have had x squared or y squared inside of your integral, and then of course you'd have to do a little bit more work to remember that x would equal r cosine theta or y would equal r sine of theta, and you'd work from there. This is a much more clever trick here. So using symmetry, especially with something like a circle, can really help you out. So let's continue on with the last problem. For a disk where you've got this constant density, m is equal to the density times the area. And what you can more or less do is say, well, the density was a constant. It was just rho. What's the area of the lamina? Well, the lamina is pi a squared for a full circle right there. So what are we really getting at? Let me just recopy this. What we could do, and we could definitely solve for rho. And that might look a little funny. You might say, well, why'd you do that? Well, that most certainly is something that we could do. And here's why this is going to be helpful. When we found our polar moment of inertia, you can see that really at the top of the screen right here. We had pi, rho, a to the fourth all over 2. But now we know what rho is in a different context. We can say it's m all over pi a squared. And look what we can do. These pi's are going to cancel out. A squared cancels a to the fourth, leaving you with a squared. So that's going to leave you with ma squared all over 2. I'm going to rewrite that and just let you look at that. That polar moment of inertia is ma squared. A is the radius of the circle, all over 2. So what does this mean? It means, if you're looking at this formula that I just circled, if we increase the mass or the radius of the disk, we thereby increase the moment of inertia. In general, the moment of inertia plays much the same role in rotational motion that mass plays in linear motion. The moment of inertia of a wheel is what makes it difficult to start or stop the rotation of the wheel, just as the mass of a car is what makes it difficult to start or stop the motion of the car moving linearly. So if we're looking rotationally, like we see right here, the bigger the R is, you can see that you have that squaring effect. But of course, mass also can influence that moment of inertia. All right, well, we've got a couple of other definitions. The radius of gyration of a lamina about an axis is the number r such that mr squared equals I. M is the mass of the lamina, and I is the moment of inertia about a given axis. So, in particular, the radius of gyration, which we'd write as y double bar, with respect to the x-axis, and the radius of gyration x double bar, with respect to the y-axis, are given by these equations. And again, I hope you can see when you've got this moment of inertia about the x-axis, again, like here's that x-axis, again, what we're trying to see is that, just as you have this I sub x, you're going to have your r, which is actually going to be a different variable. It's actually going to be a y. So we get this y double bar squared times the mass for I sub x. So that's with respect to the x-axis. That's that distance right here. So that is always a common thread that you're seeing in these last two sections. So sometimes they're going to ask you to find the radius of gyration. And, these problems can get to be a little bit long. So let's see if we could take a look at example 2. We're running out of time. We're going to have to pick this back up with our next video.